Hello, this is Lab 4 of Opti 471B called Optimal Beam Collimation and Curvature Testing. This lab goes over the use of a shear plate interferometer to test the radius of curvature of an incoming wavefront. The shear plate interferometer simply superimposes two different beams of a different optical path distance. The combination of these two beams becomes interesting when the wavefront is actually curved. The shear plate interferometer gives information about how curved that wavefront is. Furthermore, the wedged shear plate will give information about what direction that wavefront is curved in. The diagram to the bottom right shows the resulting fringe pattern for all these curvature types. In this lab, we use that type of information to test for the attributes of three different optical components: a low power lens, a low power mirror, and then a higher power mirror. Starting with a collimated source, we could add an optical component in and see how much that optical component changes the skew angle and the spacing between the fringes. This will allow us to backtrace and figure out what the radius of curvature of the wavefront is, and hence what the power of the lens or the mirror had to be. For the low power elements, this is exactly how we determined what their power was. But for the high power element, we had to get a little bit more creative. The issue is that the high power element changes the radius of the wavefront so much that you can no longer determine the fringe pattern on the shear plate interferometer. Hence, to determine the radius of the high power element, a reference lens was placed into the system. There are two positions that the mirror can be placed that will cause a back reflection that is collimated back into the shear plate interferometer. We can easily detect when the beam is collimated because that will result in horizontal fringes. Therefore, these two positions were found by finding horizontal fringes on the shear plate interferometer, and the difference of the distance between them was the radius of curvature of the high power element. The setup to perform this experiment was extremely similar to last week, including aligning a laser to the rail and aligning a pesky spatial filter with a beam expander to get this beautiful red Gaussian. Once aligned, the experiment proceeded as was described earlier. The source collimation was confirmed by horizontal fringes, and then the change in the fringe pattern was recorded using a simple ruler and protractor. The radius of curvature of the high power lens was determined to be around 400 millimeters by simply taking the difference between the two positions M1 and M2. The results of the other two optical elements require a little bit more calculation and will be done for the post-lab. This concludes the video for collimation and curvature testing. Thanks so much for listening, and I'll see you again next week.